All right, so as a little bit of review, so far we have talked about what stress means. If we're going to try to say in very rough terms what stress is trying to represent, what would you say in terms of the particles inside of a material? Okay, stress. Is stress more related to the amount of force carried, or is stress related more to the amount of change of size or shape? Okay, more related to the force, right? So one of the ways that we've talked about stress is basically a parameter that tries to get at, on average, how much force is any one bond of the material carrying, right? And the reason that we're trying to get to that is that our presumption is that any bond inside of the material can probably carry up to a certain amount, but not more. And so we need this value of stress so that we can try to figure out whether or not the material is close to breaking. Okay, so we figured that one out, and then we also figured out this other value that isn't so much related to how much force each bond carries, but rather how much each bond stretches, right? And that value that we talked about was called strain, okay? And then we looked last time at how stress related to strain, and that we can figure out information about how a material might behave by plotting stress versus strain on a set of axes after having done a material test using something like a tensile testing machine. Okay, so nice thing, a little bit later today we're actually going to let you do a lab and get to experience at least part of that process of testing a material. But before we get to that, let's talk a little bit more about the idea of determining how much a body might deform under an axial load. Okay, and I'm trying to use certain terms that will come up now and then, but when we talk about an axial load, what is that? Okay, first of all, load is a lot of times a word we use for force. So force and load are fairly interchangeable in terms of how we use those, but then it's a force or load that acts down the axis of a body, which is why we call it axial stress. But basically what that means is you kind of imagine something where generally what we can kind of think of is that the long axis is the axis down which the force is acting. It doesn't have to be, but it's basically just a force that is applied along the length that you are trying, in the same direction as the length that you're trying to determine how far it changes, right? So you're saying apply a force in the same direction as the original length, and we're going to try to figure out how far it changes. That was part of our discussion from the last time that we met, but we haven't really come up with a good unified formula for what this little delta is going to be if we have a piece that's kind of a macroscopic sized piece that has a force of F applied to it. We don't have a formula yet that exactly just gives us that change in length, given other things that might be easy for us to find. So what I want us to do is work together and try to see if we can think of the different pieces that would need to bring together in order to come up with what a formula would be for this axial deformation delta. Okay? So let me actually start here. We know we're trying to get delta, right? Did delta show up in any of our other formulas that we've talked about up till now? Okay, where did it show up? Okay, so delta was part of our definition of strain, right? So if we want, we can take that and just try to remember that definition of strain. So strain was going to be equal to what? Delta over L, where L is what? Okay, so on this body, we could probably write L right here, and that would be fair enough to say, right? That was our original length of L, and we're saying it will deform under some force F, and we'll have delta over L gives us strain. Okay, so here's a question. If I take a body and I start stretching it, is it easy for you to look at that body and tell me how much strain is in it? Like, can you examine it and say, I think you're putting 0.00001 amount of strain in that? Is that easy for us to just tell? No. Okay. So for us to be able to use this directly to predict delta, it's not quite enough yet, because the epsilon term there is not something that's easy for us to just tell what it is based on either looking at a part that's already being loaded or anything else really. So tell you what we can do, we can actually go ahead and solve this for delta. If I solve it for delta, what does that end up being? Epsilon times L, right? But it isn't quite what we're asking for yet, because it says, can we predict delta using relatively easy to find information? So we need something to replace epsilon. Like what? Okay. Someone suggests Young's modulus, the modulus of elasticity. Okay. And how did we end up defining that modulus of elasticity when we met last time? Okay, we said that the modulus of elasticity was going to be equal to stress over strain in the elastic region of the material. So already what we're going to say is that what we develop here in terms of the deformation of this body is only good for the elastic range of the material. Okay? But I can take this and I can solve it for epsilon if I so desire, right? And what would that give me? Okay, heard someone tell me epsilon strain should be equal to sigma stress over elastic modulus. Okay, by the way, this is a little sidebar real quick. Sometimes this relationship, sigma equal to elastic modulus times epsilon, stress is equal to elastic modulus times strain, this relationship is sometimes known as Hooke's law. I feel like just a bunch of people wanted to get their name attached to these things. So I don't know. I don't know what the story is on that, but it's the same relationship, right? Anyway, that's a little bit of a side note. So epsilon equals to sigma over E. Can I use that in my previous equation? Okay, so what I can say now is that delta should be equal to stress over elastic modulus times L. Okay, so now I'll ask the same question. Stress, sigma. Is it easy to just look at this thing and tell how much stress is in it? No, but stress is going to be related to how much force is being applied, and that's one of the things that we wanted to be able to say. It's going to deflect a certain amount under a certain amount of force, right? So what should we do to get force into this equation instead of stress? Okay, the definition of stress is equal to force over area. And so that tells me that my delta then is going to be equal to F over A over E times L. Okay? And I can clean that up a little bit, and this ends up just being FL over EA. Okay? And you might have been able to predict that from the beginning, because these things don't tend to deform very much under a certain amount of load, and so it doesn't surprise us that it deflects a flea, right? Should have been able to tell that from the beginning. Okay? FL over EA. I know that's corny, but now you won't forget it. Okay? It's FL over EA is how much the thing will deform, how much it will change in length under a force of F. Okay? What's A? Okay, for whatever shape this thing is, you just have to figure out what its cross-sectional area is, A, in order for this to work. Okay? Now let me actually put a couple other notes on here. This works as long as all of these values are constant. Right? So within that range of material, within that length of material, all of that material is experiencing an axial force of F, right? Regardless of where I would make a cut through that material, it's all got to be carrying that force of F, regardless of what particular cross-section I cut through, it's all carrying F, right? It all has the cross-sectional area of A, right? I can't have a variable area in order for this to work as is, okay? And then E, right? My material properties can't change somewhere halfway along the length of this body, okay? I'm going to skip it for this particular lecture, but there are some things we can do to handle variable quantities in those parameters. And so, you know, one of these days maybe I'll do another lecture about that, but for now we're just going to let each of these quantities be constant values. Okay? All right, so my next question is, what if you have a rod, because that's a lot of times what we call a member that's shaped like this, what if you have a rod that instead of having just one cross-sectional area to it, or just one you know, elastic modulus, you know, like a kind of type of material or whatever, what if you have multiple, okay? I'm not quite going to the level of saying we have a fully variable, you know, amount of cross-sectional area, but what if you have what we would refer to a lot of times as like a composite rod? In other words, something like this. Okay? So let's say we have you know, more than one force being applied onto this piece. Okay, it can be made of two different kinds of material. All right, so to indicate that, let me just sort of label over here. Maybe this one has a elastic modulus value of E1, and over here maybe this one has an elastic modulus value of E2. They can be two different kinds of material. Right. They also could have different lengths, right? So let's say over here, maybe this piece has a length of L1, and this one has a length of L2. Okay, based on how they're drawn, you might also suspect that they might have different cross-sectional areas, right? So this one up here maybe has a cross-sectional area that is like A1. And over here, let's say this one has a cross-sectional area that's A2. I'm super creative with my names. You should meet my kids 1 and 2 sometime. Just kidding. All right, so my question is, if this is all the stuff that we know, how do I figure out how much point A at the end of this rod is going to deflect under these conditions? How would you think we should go about figuring that out? Well, let me ask you this. If you focus just on segment AB, could you tell me how much just segment AB changed in length? Right? If you were to chop off segment AB and just look at it all by itself, okay, how would you determine how much just that segment would deform? Okay, same way as we did up above, right? All you got to do is figure out how much force is being carried in that member, right? And when you do, then you should be able to come up with maybe a delta, maybe we'll call it delta AB, for how much does this thing deform from point A to point B. Okay. And let me ask you this, how much force does that segment between A and B carry? How would you determine that? Okay, I'll tell you what, I'm going to be really persnickety here and say I'm going to assume I don't see anything at all in terms of what that should be holding. Here's what I should do if I need to figure it out. What you do is you make a cut in that member. Okay, you say, I'm going to chop that member not at either of the ends, but somewhere in the middle. Okay, like if I feel like there's no changes in any of the parameters happening from A to B, then chop somewhere in between from A to B and do a free body diagram of just one side. Something like this. Okay, and I have a force again of F sub A over here, which would be one of my probably given values in any problem that would be like this that I'd be trying to solve. And what I'm trying to use is that value to determine what is the internal force inside of this body that reacts against F sub A to keep that little tip of the body in equilibrium. All right? And let me call that F1. Okay, because I've labeled all the other things 1. What I'm coming up with there is the amount of force that is being carried in segment 1. Okay? Now, I've done this extremely formally here, where I've gone ahead and done a free body diagram with F sub A and F sub 1. And what do you do with a free body diagram? You write equilibrium equations, right? So, you know, the only direction that really has any interest to us is horizontal. So if you sum forces in the horizontal direction, what do you find? Okay. So my point with this is I'm trying to be pretty careful and say, when you find the forces that happen in each segment of the rod, make sure that what you're doing is finding the actual force in that segment and not one of the forces applied to one of the ends. Even though it turns out for this front one, it does turn out to be FA, I'm still going to express this like this, where I do F1 times L1 over the elastic modulus of that piece, E1, times A1, the cross-sectional area of that piece. Okay? And here's why I'm trying to do it that way, is look what happens when I try to do the same thing for segment BC. Okay? What is the force carried in segment BC? Okay, well, let's do the same thing again. I'm going to do a little free body diagram of everything to the right of a cut that I make right here. Okay, kind of think about making a cut in that member right there at that location. And I'm going to do a little free body diagram of that over here. I'll make it a little smaller so we can fit it in over here. Okay, so there's a little chunk from B to A, but then, you know, we have this other part, something like this, up to where we made the cut. Okay, and now I put FA on here. The reason I showed FB and I showed it as 2 places of FB over 2, I was trying to help you have a good feeling about that we're not flexing this rod. We're not trying to, you know, flex it. We're trying to put a force on it that is ultimately directed along the axis of the rod. So I showed it as 2 FB over 2s, right? So what would the total force be that would be acting at B then? 2 times FB over 2 would be just FB, okay? So figured I'd explain that. All right, so let me put those on here, FB over 2 and FB over 2. And then I'll put over here one force that reacts against all of that, and I'll call it F2. Okay? Now what do you think I'll do with all of this? Okay? I'll sum forces in the horizontal direction, and when I do, what do you think I'll find for F2? Okay? it's the sum of those two values. Or another way of thinking of it is it's the amount of force that has accumulated as we've moved through the rod, right? So we started with an FA, and then we added another force of FB, and so now that's how much force we have for F2, okay? So I'm still going to write this as F2 L2 over E2 A2, right? But I want you to see and sort of understand that when I'm talking about F2, I have to look at how much force is accumulated coming up to that cross-section in the part. Okay? Now, I've done this so far. I've come up with how far BC will have changed in length and how far AB will have changed in length. What's my overall change in length that I have labeled delta A up there? Okay, you add those two together because what you're doing is you're saying the starting point B for segment AB is going to shift to the right a little bit under the load, right? And that it will shift to the right. Point B will shift to the right by this, this amount that I have written over here on the right. To figure out total how much point A moves, I have to account for not only the amount that segment BC changed, but also how much AB changed, right? And if I add those two changes together, then I'll get the total amount of change at point A, okay? So when I write this down, I'll say delta A is going to be equal to F1 L1 over E1 A1 plus F2 L2 over E2 A2. Okay, and just keep in mind F1 and F2 are how much force each of the segments that they are associated with are carrying. And that's not always easy to figure out. It's one of those things where you sometimes have to do a step and figure out how much each individual segment is carrying. But that's what they represent, F1 and F2. Yes, sir?
So would you be counting FA twice? Since F1 and F2 both?
Okay. Question is, wouldn't you be counting FA 2 times? Okay. And my question for you is, maybe we are. Is that a problem? Are we worried about that? Okay. Maybe another way of saying is, does it make sense that it would have to count as part of the load that segment BC is carrying?
Well, it's because we're doing equilibrium conditions for the body.
Okay. Yeah, so think of it this way. What if we do make a cut right here at B and just draw a free body diagram of segment BC, right? So here's just segment BC all by itself. Okay. And my question for you is, once we put the, not that direction. Once I put FB over 2 here, okay, and FB over 2, and then what should go right here once I've chopped off that little segment? Does the force that I apply at A transmit down the length of AB, and should it attach right there? Okay. So I think what we're seeing here then is that the total amount of force being applied to that segment is FA plus FB, right? And it's not a problem that we're counting it again, because that really is the amount of force that's being carried in that segment. So yeah, that's part of what I was talking about earlier, that the force will accumulate as you go down the length. Okay? All right, so that's what delta A is this sum. My next question for you is, did I have to limit this to just 2 segments? okay? All the principles that I showed up there look to me, at least, like they would hold for as many segments as I wanted to stack up. Do you agree with that? Like I could have put a third segment on there, and as long as I figure out the force carried in that segment, and the length of that segment, and the cross-sectional area of the segment, and the elastic modulus of that segment, right, I can figure out the amount of change of length of that segment, and then if I just change, if I add up all of those changes in length, that gives me my overall change in length. You got a question? If you had a cone, you could do an integral, okay? And that is the exact thing I said I'm probably not going to get into today, but we could do that problem, and that would be an interesting one. So it's very tempting. I would like to do it, but I'm going to leave this, you know, it's an interesting topic that isn't officially part of what this class is supposed to cover, so, you know, I always have to watch getting too much extra stuff. All right, what I was going to get back to is this setup, this construct of how this equation works is expandable to n segments, however many segments you want to do. And what would the math have to look like if we wanted to set that up? Okay, let me maybe call delta, I'll call this delta total is going to be equal to what? This is kind of generalizing, right? The sum. So the sum, and what would the sum look like? We'd need an index to sum things with, so I'm going to use I equal 1 up to n being the number of segments that we have to think about. And then what do we put in here? Fi times Li over Ei times Ai, where you basically use the little index to indicate the force, length, elastic modulus, and cross-sectional area for each of the segments. Okay? Awesome. Now, shall we do an example problem? Since I'm driving, I say yes. Okay, so here is our example problem. I have a composite rod composed of titanium on the left segment, aluminum in the middle segment, and steel on the right segment. Okay? And this says, how far does point A move when the loading scenario shown is applied? Okay? He says, so it looks like we're compressing the aluminum section. Okay? I could believe that, but let's actually show ourselves whether or not, you know, what exactly is happening with this setup. Okay? The one that is actually maybe more confusing is what exactly is happening with the titanium section. Okay? Well, let's get into that and figure it out. Okay, one of the reasons that I'm showing you this is I want to show you a technique you can use to determine how much force is going to act in any of the segments of the composite rod. Okay? And it's relatively obvious once you see it, but it is also one of those things that if you don't know this exists, you might spin your wheels a little bit. What if we just drop a few vertical lines down like this? Okay. And we understand that the amount of force that's being carried in any of the segments, the only place it can really change is any of the spots where a force is being applied, right? So I've got a 40 kilonewton force. That's a place where the force value could change along the length of this member, okay? or where the 30 kilonewtons is being applied. That's another place where the force could change at that location, or where the two 80 kilonewton forces are being applied. That's another spot. Okay? Good so far? And what I'm going to do here is make like a big old set of axes, where this axis, I'll call it X, kind of a spatial axis along which this thing acts, but on the vertical axis, okay, I'm going to call that force, or just F, and I'll put that in kilonewtons. Okay? And I'm a little concerned about where exactly I drew this axis, so I'm going to move it just a little bit. Okay? Because I want it to be at least roughly kind of to scale. All right, it says 40 kilonewtons is applied at point A. Let me ask you this. How much force is applied or is carried in material that's to the right of point A? Zero, someone says. How do you know that for sure? There's no material there, so it better not be carrying load, right? So when we're to the right of point A, we better be starting at 0 for our amount of force that we're carrying. Do you agree with that? Okay. And then once we hit point A, we have this 40 kilonewton force that's being applied right there. And I'm going to suggest that because that arrow is to the left, meaning it's going to kind of compress that member right there, I'm going to count that as a negative force. Okay? And so what I'm going to do is draw a roughly 40. Tell you what, I'll just make the squares worth 10 apiece. Okay? So I'm going to go down by 40 kilonewtons. And let me go ahead and label that as well. Okay? I'll move over to point B. Now what happens at point B? Okay? I did this on purpose so you could see a few different ways of representing some of these forces. This comes up a lot in these axial kind of problems because, again, like I said earlier, we try to represent them that it's obvious that we're not also inducing a flexure in it. We're trying to put just an axial force in it, so we a lot of times will split the force up and show two different ones like this so that it doesn't imply that you're flexing it also. Okay? But if you see it like this, where it shows two forces like that with a bracket across them and a single number, what do you think how should we interpret that? That's 30 kilonewtons distributed across those two application locations. Okay, they could be 15 each, right? Okay, but it's 30 total. And so, and they're to the left, right? So that since they're to the left, just like the last one I had, what I'm going to do is show that accumulating another 30. So how much force is going to be carried in that next segment? Negative 70 kilonewtons. Okay? Now contrast that sort of figure thing where it's got the bracket across the two forces, and I'm showing another one here where I show two forces, each of them labeled 80 kilonewtons. What do you think a good way is to interpret that? That is 80 kilonewtons each. Okay? And so I'm trying to show you some of the tricks about how some of the problems you might see are written. You got to make sure you interpret it properly. And it makes sense that it works that way. I just wanted to say it so that you'd hear it. Okay? But I've got 80 kilonewtons each, which means it's a total, someone said, of 160 kilonewtons. Right? To the right or to the left? To the right, which is the opposite direction of the last two that I just showed. So I need to now rise here by basically 16 squares, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? So how much force is carried in segment CD? Okay? Yeah, we had to go from negative 70 up to 90 kilonewtons. Oop, I already have kilonewtons labeled on the left, so I don't need to put it again. Okay? And all you're doing here is you're acknowledging that as you move along the length of a rod like this, your forces accumulate, right? And the easiest way to do these is to try to start at an end that is free. What do I mean by that? Okay, zero material after it, but really what that means is if you go to point D, for instance, I'm showing there's a wall that's going to be able to react something over there on the left side, right? I'm showing the right side with nothing like that, so it's free to move. Okay, so it's always easiest to start these, if you can, at an end that is free, because you can start at 0 if you have an end that's free. Once we get to point D, we've got 90 kilonewtons there. Where does that 90 kilonewtons come from? On the left end. All right? What did you say? Okay.
Whatever this rod is attached to something.
It's attached, right, it's attached to that fixed side over there at D. So D is applying a 90 kilonewton force, right? That wall at D is applying a 90 kilonewton force to this composite rod, right? In what direction? In other words, if I was going to, instead of showing this as a wall, right, instead of showing it like that, I was going to actually show it as a force. Oop. Okay. As I was going along, anything that pointed to the left, I counted as a downward thing, right? And anything that pointed to the right, I counted as an upward thing. So when I get to location D, does it go down or up as I'm going from right to left? Down. So it looks to me like the effect of the wall at point D is going to have to be to the left. Okay? All right. So that is honestly the most tricky part of most of these types of problems, is making sure you know how much force is carried in each segment. All right. Once you know how much force is carried in each segment, how do you come up with how far point A moves, assuming point D is fixed? Okay. Well, now we have to apply our other things that matter for this question. Ultimately, what we're trying to do is determine my total change in length, or change in position, I guess, of point A. Okay? And it's going to be based on how much each segment changes, right? So how much does segment CD change? What's my formula I need for that? FL over EA, F being 90 kilonewtons. Question for you, tension or compression? Okay. When I drew my little chart here, I drew it according to compressive being negative, right? You can see there at point A, the 40 kilonewton force is going to try to compress the steel piece that's right there. Right? So it makes sense from that end. Also, at point D, it makes sense that if you have a 90 kilonewton force going away from the rod at point D, that would tend to try to stretch it from C to D. Right? And it does turn out to be a positive 90 kilonewtons there. So my recommendation is when you're writing these equations, try to write them so that your elongation forces, your tensile forces, are all positive, and your compressive forces are all negative. Okay? So 90 kilonewtons times what? 14 centimeters. Okay? What do I need now? Okay, I need the modulus of titanium, someone says. Well, look at that. I happen to have it. Ask and you shall receive. Titanium alloy, 930. Oh, that's, what is that I just looked at? Okay, but that's elastic strength, right? Is that what I want? No, I want the modulus. So I need to slide over a little bit further. Modulus of elasticity. Notice the units, GPA. Okay. 96 GPA. What is GPA? Gigapascals. Okay. 96 gigapascals. Okay. What next? Area is going to be based on pi times, what's the diameter of that segment? Okay, the radius would be 6 millimeters, the diameter is 12 millimeters. Yeah, you can do it either way, but I was planning on doing diameter there. And that would be squared, right? 12 millimeters squared over 4. Okay? Awesome. That's how much segment CD contributes to the overall movement of point A. What about BC? Negative 70 kilonewtons times 17 centimeters. Okay. Over the modulus of aluminum. What kind of aluminum, someone wants to know? Well, let's look in the reference material here real quick. True. He says it just said it was titanium. It didn't say it was titanium alloy. All right? Have you guys ever seen something that was built of pure titanium? Okay. Just checking. All right. Most things that are titanium are some kind of a titanium alloy. All right. Now, we need the modulus for aluminum. All right. And I left it a little bit vague on purpose here, but let's look at these aluminum values over here. We've got, for cast aluminum, we got 71. Wrought aluminum, 2014, we got 73. 2024, we've got 73. 6061, we've got 70 GPA. I wanted you to see there, within that material family, there's not very much variation. Okay? What do you want to use? The weakest one? Okay, how would we know which one's the weakest? Okay, remember, this doesn't have anything to do with weak or strong. This has to do with stiff or less stiff. Okay, so over here is where you would deal with what is stronger. So which is the strongest kind of aluminum? Elastic strength looks to me like it's saying that your 2024 T4 might be one of your stronger aluminum preparations. Anyway, why don't we use 73? Okay. So 73 GPA. Okay. And what's the area? Pi. The diameter is 19 millimeters squared over 4. And what's the last term? Okay. Negative 40 kilonewtons. Length is 11 centimeters. And in the denominator, see, this is steel. Let's go back in the reference material again. So check out these moduli of elasticity. Okay, structural steel says it's what? 200 GPa. Says it goes up to 210 GPa for some of these other steels. It's got another steel down here, 4340, at 200. What's the strongest of those? Okay. That 4340 heat-treated steel is pretty strong, isn't it? How do you know? See this value right here? That's pretty high relative to some of your other steels, right? Now, we're not trying to answer a strength question right now, except this whole discussion that we're having about how much this rod deforms only works insofar as the rod stays in its elastic range, right? Our whole discussion here is predicated on that rod not deforming plastically. Why don't we use our most strong value for this, just for the heck of it? Okay, that way maybe it represents a 4340 heat-treated steel, and we have less concern that it might go plastic. Maybe. I mean, we don't want it to plastically deform, right? And that'd be an interesting thing for us to check as well, is to see whether or not any of these segments plastically deform. Okay, so let's put in here 200 GPa. And down here, pi times 8 millimeters squared over 4. All right. Now, some of you might be cringing a little bit looking at all of those units up there. Are you? It's okay to admit it. All right. What do we need to do with all those units? Okay. Do we need to convert them each time we do one of these calculations? Or could I do a once and for all conversion across the whole thing? Okay. It depends, right? For this one, I can do a once and for all conversion across the whole thing. Why is that? Each term has the same types of units in them, right? So if I multiply all the units together in any one of those terms, it's going to have the same product of units in any one of those terms. So if I figure it out for one of them, I figured it out for all of them. So how do I go about doing this unit conversion then? What's the first one you want to convert? Kilonewtons. So there's 1,000 newtons in a kilonewton, right? The next one is, okay, 11 centimeters, but it's, a centimeter. How many centimeters in a meter? 100. Okay. What about GPA? Okay. So we could do 10 to the 9th pascals in a gigapascal. Okay. And then what about millimeters squared? Okay. And multiplying by all of that will get us to what? Tell you what, let's go through and cancel them out. There's kilonewton gone. Okay. GPA is gone. Some of you know what that's like. Okay, there's centimeters gone, right? I have meters squared in the denominator. Okay. And a meter in the numerator. Is that right? But what's a Pascal? Okay, because some of you might be looking at that going, well, what I've got so far is a, 1 over Pascal meters. Not 1 over, excuse me, newtons over Pascal meters. Okay? We'll notice here that a Pascal is actually a Newton meter. Excuse me, Newton per square meter. Sorry about that. Right, and that's a Pascal. So the Pascal goes away. Right? So that actually knocks out my meters squared right there, and what am I left with? And it also knocks out the Newton. And I'm left with meters. Okay? So a lot of times you don't have to do this, every single time you do a calculation like this, but it's good to do it at least once to make sure that you feel comfortable that what you think is supposed to happen with all the units really does. All right. So, shall we punch all this in? All right. So let's see. We've got 90 times 14 over 96 times pi times 12 squared over 4 plus or minus. I could put minus here, right? Why? So I've got that negative 70 there, so I'll put minus 70 times 17 over 73 times pi times 19 squared over 4. Okay. Minus 40 times 11 over 200 times pi times 8 squared over 4. Okay? And the answer I get, I'm going to go ahead and hit equals. Answer I get is nothing just yet, because whatever I get there, I need to apply all of these conversion factors to that. Okay? So I'll hit equals. I get this result. What do I need to do to the result? Okay? Multiply by, okay? Up there in the numerator of this thing, it looks like I have another fraction that is just 1,000. Okay? I'm intentionally, not doing any of it in my head, right? 1,000 over 100 would be what's in the numerator there. Now what's in the denominator? Okay, so I've got 10 to the 9th. Okay, I don't need any more there. What's in the denominator down here? 1,000 squared, right? And I get 1.479 times 10 to the minus 4th. We said earlier that was going to come out in meters. Okay? What if I hit my ENG, or actually might be better for me to put in like something like this, right? 0.0001478. Okay? Or if I do this, then that number should be what? That's millimeters. So it's, in other words, point A moved by 0.1478 millimeters. Okay. To the right or to the left? Okay? Someone has a vote for move to the right. Okay? Why would you vote for to the right? Okay? So all of our compressive forces were ones to the left, and all of our tensile forces were one to the right. Okay? Ones to the right will tend to move the thing to the right, and those were counted as positive. Ones to the left will move it to the left, and those are counted as negative. I come up with a positive result here. I come up with a positive result. That means point A will move to the right. It will move to the right even though segments AB and BC both carry compressive force. Okay? The reason why is that there's enough of a tensile force between C and D that it stretches that segment more than the combination of AB and BC compress. All right? Cool. Any other questions? Yes?
So what we calculated is the net change of the entire rod, but segment AB is a completely different average.
Segment AB is based just on this term.
So we would have a compressive and its length would actually shorten, or its delta would be negative.
Right. So, that term right there arises from this segment. This term right here arises from this segment. And the last term arises from that segment. And so the only one of those that was positive, i.e. elongating, it would be the first term on the left there. But it had enough of a magnitude to it that it sort of overrode the other two, and it ended up actually moving point A to the right. Okay? Sounds good. No other questions? All right, let's get to our lab.